This video discusses applications of polynomial equations. Our first example, the height of a box containing HP Laserjet 3 printer cartridges is 4 inches more than the width, and the length is 9 inches more than the width. If the volume of the box is 630 cubic inches, then what are the dimensions of the box? Well, the first thing I would do is draw a box. We're told that the height is 4 inches more than the width, and the length is 9 inches more than the width. We don't know what the width is, so we'll call it just x. The height is 4 inches more than the width, so we can call the height x plus 4. And then the length is 9 inches more than the width. That's going to be x plus 9. The other piece of information we were given is the volume of the box. Since they gave us volume, that tells us that we're going to want to use the volume formula for a box. That formula is length times width times height. We have the volume, we have the length, the width, and the height. We can write ourselves an equation. Our volume, 630, is going to be equal to the length times the width times the height. Now, I did put the width first just because we like the monomial factors first, and that's no big deal since multiplication's commutative. Next, we'll multiply this all out. That gives us 630 equals x times x squared plus 9x plus 4x plus 36. That's 630 equals x times x squared plus 13x plus 36. Distributing again, 630 equals x to the third plus 13x squared plus 36x. This is a polynomial equation. To solve a polynomial equation, we want to set it equal to 0, factor it, and then set each factor equal to 0 and solve. Setting this equal to 0, we get 0 equals x to the third plus 13x squared plus 36x minus 630. Well, I want to factor this. Right away, I would try factor by grouping. I always try grouping when I have 4 terms. Take out an x squared. But unfortunately, the common factor in my second 2 terms is 18. And when I factor out an 18, I do not get a common binomial factor. So grouping's not going to work, but I always try it because it's certainly easier than checking a bunch of zeros. Since it didn't work, well, we got to check a bunch of different zeros to find actual zeros to give us some factors. We need some numbers to get started. So we want to create our list of possible rational zeros. To find possible rational zeros, we take the factors of the constant and divide it by the factors of the leading coefficient. Our constant is 630. That's a big number. It's going to have lots and lots and lots of factors. I do not recommend trying to write out all the factors. I would just start with some of them, and if none of them in that list worked, well, then I'd make my list a little bigger, and if none of those worked, I'll get another list a little bigger. Also notice that our leading coefficient is 1. So we're doing the factors of the constant divided by the factors of the leading coefficient. We're always dividing by 1, so really we're just looking at factors of our constant. Also think about what x represents. Looking at our diagram, x is the width of a box. When we discuss the width of a box, we only reference it as a positive number, never a negative number. Therefore, we don't need the plus or minus when listing our possible rational zeros. We only want positive numbers. So let's list some positive numbers that are factors of 630. Factors include 1, 2, 3, 5, 6, 7, 9, and 10. There are a bunch more in there, but I think that's a good enough list to get started. And we'll start testing some of these possible rational zeros. I always start by checking 1. I do the shortcut of adding up the coefficients. So if I look at the coefficients of my positive term versus my negative term, when I add that up, I definitely do not get 0. So positive 1 is not going to be a 0. So that one's out. Let's check 2. Synthetically dividing 2 in. We get a remainder of negative 498. Since this is not 0, 2 is not a 0. Now that remainder was pretty big. Negative 498. I'd be inclined to kind of jump to a bigger number. Let's jump to 5. Since our remainder is a large number, negative 498, I'd be inclined to not go to 3 as my next try, but jump to a little bit bigger number. Let's try 5. So synthetically dividing here. This time we do get a remainder of 0. So that means that 5 is a 0, and from that 0 of 5, we can get a factor. So let's head back to the equation and start factoring it. Since 5 is the 0, x minus 5 is the factor. Our next factor is going to be quadratic. 1x squared plus 18x plus 126. Once the largest factor is quadratic, you don't need to check zeros anymore. We can use one of our other techniques. I'll start by trying to factor this, but there aren't two numbers that multiply together to be 126 and add together to be 18. Since we're solving this, I'm not worried about getting down to linear factors. I just need answers. So we're going to apply zero product property and solve each equation individually. Our first equation, we get x equals 5. Our second equation, since it doesn't factor, is going to require quadratic formula. X equals negative 18 plus or minus the square root of 18 squared minus 4 times 1 times 126 all over 2 times 1. Simplifying, we get x to be negative 18 plus or minus the square root of 324 minus 504 all over 2. That'll be negative 18 plus or minus the square root of negative 180 all over 2. Notice our radical. We have a negative underneath of a square root. That's going to be an imaginary number. This is an application problem. X represented the width of a box. You can't have a box with a width that's imaginary. It's not a real box then. Therefore, this solution gets thrown out and our only solution for X is 5. Since it is an application problem, we need to make sure that our answer makes sense for the context of the application, which is what we just did, and we threw out the imaginary number. We need to make sure that we have answered the question and included any necessary units. So let's go back and look at what the question was. They ask us to find the dimensions of the box. So far, we have not done that. What we found was X, which is the width, but we also need the height, which is 4 more than the width, and the length, which is 9 more than the width. So our width, which is X, is 5. Our height is X plus 4, so that's going to be 9. And lastly, our length is X plus 9, so that'll be 14. And then be sure to include your unit. Each one of these is inches. One more application problem. We've actually done ones like this in previous sections. We want to find a third degree polynomial function that has zeros of negative 1, 2, and 4, and f of 1 equals 3. We saw problems like this when we were discussing graphing polynomial functions. Now recall that the zeros, these give us factors. And the f of 1 equals 3 will be used to find our leading coefficient A. It said it's going to be a third degree polynomial, and they provided us with 3 zeros. That tells us that there's not going to be any multiplicity on any of the factors. Let's start writing our polynomial. P of x is equal to, well, we're going to have a leading coefficient of A, which we'll find later. And then each zero gives us a factor. So the 0 is negative 1. The factor is x plus 1. 0 of positive 2. The factor is x minus 2. 0 of positive 4. Factor of x minus 4. Now that we have that, we are going to plug in f of 1 equals 3 to solve for A. So subbing 3 in for y and 1 in for x. This becomes 3 equals A times 2 times negative 1 times negative 3. That gives us 3 equals 6A. Therefore, A is 1/2. We'll plug 1/2 in here from A, and that'll be our final answer. Our polynomial function is P of x equals 1/2 times x plus 1 times x minus 2 times x minus 4.